Hi, everybody. Welcome to the Virginia Tech Carilion Wilderness Medicine Journal Club series. This is August 2024. Our topic this month is freediving. We're going to discuss two articles, and then we're going to transition to a presentation by one of our guest experts. I'll be serving as host, introducing people as we go, and then I'll do my best to sort of hang out in the background and chime in intermittently. So starting off, we're going to begin with a review, kind of all-encompassing article. Jackson Anderson is going to be our first presenter. And Jackson, you already have your presentation up. I'm going to mute myself and please take it away.
Cool. Hey everyone, I'm Jackson Anderson. I am a second year EM resident at UT Southwestern. I went to med school in Miami and I'm a horrendous freediver because I used to go with my friends who would try to go spearfishing, and I was always the guy just holding gear at the surface, just waiting for them to come back up because I was so bad at it. But it was really interesting to read about this. So, the article that I'm reviewing today is titled Breath Hold Diving, the Physiology of Deep Diving and Returning. The authors are at the top there, and it's mostly out of Croatia. And then there's a collaboration with some Canadian physicians as well. Um, so just like kind of some background to breath hold diving. So like historically, it was done in largely in the Mediterranean for collecting sea sponges, for collecting sustenance, and also for salvaging shipwrecks. And then, historically, I mean, I learned about this in like elementary school. I don't know if that was just my teacher was really into it, but Japanese pearl divers and Filipino pearl divers it was like a big subset of society. They're still around today. The female pearl divers are known as the ama in Japan, who would dive down and then they'd crack open crustaceans and see if they could harvest pearls from them. So that's kind of some background on what it was historically. Now, what it has become more traditionally today, I mean, still some people do it for sustenance and for, like harvesting like different sponges, different types of food, but there's also this recreational aspect that has come into play as well. So, just some interesting statistics to start with as well. So, at Dangerous Sport, in 2017, there were 52 deaths alone within that year, which was the highest number recorded. I think they said since like 2003 or 2004. And then as far as depth records go, I was looking these up and I was kind of amazed. So there's different styles of free diving. Constant weight is like kind of the typical one that I would imagine, where you're kind of just going down with fins and a weight belt. And the records for that were both set last year at 436 feet for men and 403 feet for women. But then no limit diving, which I read about and thought was absolutely an insane sport, is essentially you are tied to a weighted sled and shoot down pretty much as deep as you can go, and then you inflate a bag that'll bring you back to the surface. The record for men was set in 2007 by Herbert Nitsch, who went 700 feet deep. And I kind of a wild story that when this guy got to the surface, he was immediately helicoptered to a hyperbaric chamber and ended up having multiple infarcts from gas emboli. And then Tanya Streeter set the record for 526 feet a few years after that. So just some interesting stats. So as far as the physics of breath hold diving go, in general, at the surface, we are exposed to 760 millimeters of mercury of pressure, or 1 atmosphere of pressure, and then every 10 meters that you go down, you increase the hydrostatic pressure increases by 1 atmosphere. So at 10 meters you're exposed to 2 atmospheres, at 20 meters you're exposed to 3 atmospheres. And this how this plays into breath hold diving, like with gas laws play a big part in all this. And I had to review some of this because I had not heard Henry's law in a long time. But essentially Henry's law plays a big part here, as you increase pressure, you're also going to increase solubility of gases. So as you go deeper, you're going to have more precipitation of those gases into tissues, like nitrogen, especially is like one of the big ones that we talk about a lot. And then Boyle's law, as you're going to go deeper, as that pressure is increasing, volume we're going to reciprocate is as the pressure goes up, and volume is going to reciprocally decrease, and it's like a 2-to-1 ratio. So if you go down 100 meters or so, you're having what your volume was. So for lung volumes, this is particularly important because you're essentially just compressing the lungs with all this hydrostatic pressure as you go down. Um, but and I can't see my notes here for some reason, but I think I'll be okay. But the article basically walked us through the phases of a breath hold dive. So those phases include the first 20 meters of the dive, the passive descent past those 20 meters, the maximum depth, ascent, the last 10 meters, and then being back on the surface again. So before all this, we're prepping for a breath hold dive. So one of the big techniques is something called lung packing or glossopharyngeal insufflation, which essentially is taking a really deep breath, filling up your lungs as much as you can, and then closing off your glottis, and then trying to literally use your tongue to swallow more air so that you're increasing your lung volume and your total lung capacity as much as possible before the dive. Then there's also like a variety of lung stretches and thoracic stretching exercises that divers will do. And essentially the goal of this all is to increase your total lung capacity. So first 20 meters as we're going down. So the second you get in the water, you have your diving reflex. So you're going to increase your parasympathetic activity. So your heart rate's going to go down. But then at the same time, you're also increasing sympathetic activity with vasoconstriction. Now, one of the things that can happen in these first few meters that they've talked about is cardiac dysynchrony. So essentially, because you're getting so much parasympathetic and sympathetic kind of fighting each other, your heart is essentially pretty confused, and it doesn't know if it needs to go fast or it needs to go slow, and you are more predisposed to potentially developing some dysrhythmias, which they did some really interesting studies, I think in the 1960s, where they had divers go down wearing like Holter monitors essentially to record electrical activity to see how this diving reflex was going to affect dysynchrony. And then additionally on the surface, you're going to get all kinds of different fluid shifts, blood flow redistribution, altering of your hemodynamics and autonomic activity, as we kind of already discussed with the diving reflex. So that's going to happen in about the first 20 meters. And why the first 20 meters is important is then you're going to get to a point around 20 meters, and it depends on body composition, weights you're using, how thick your wetsuit is, all kinds of different things. But around 20 meters is where you're going to find that neutral buoyancy. And what that neutral buoyancy means is this is where the weight of the water column on you and your buoyancy trying to go back, and the air in you trying to go to the surface, this is where it cancels out, and you're basically floating there. The net force is zero, and you're just kind of hanging out at 20 meters, and you're not going to be moving much. Now below that, you get negative buoyancy, and that's the point where the weight of the water column is essentially going to be pushing you down. And at this point, your peripheral vasoconstriction is maximized because of that initial sympathetic surge during those first 20 meters. So now, as we keep going down, we're starting to talk about lung compression. So like we were talking about with Boyle's law, that as pressure is increasing, volume is going to decrease, volume of the gas in an enclosed space is going to decrease. So your lung volume is going to decrease. It's going to be basically halved. So around 18 meters, you'll start having some collapse of the basal segments of the lungs. And then your lungs will collapse to the residual volume. So basically the minimum volume in your lungs, you'll be reduced to that around 40 or 50 meters. And at this point, because of all that collapse and all of that hydrostatic pressure, your alveolar pressure goes up really high, leads to tissue strain, can lead to some capillary shearing of the capillaries, and can lead to pulmonary edema. And we'll kind of touch on that more later because that's a bigger issue in ascent. And then at this point too, because your lungs are very compressed, but you're getting a lot of vasoconstriction in your extremities. You're getting vasoconstriction to organs that you're not using as much, so your kidneys and skeletal muscle. And so a lot of your blood is then essentially shunted into the thorax. And so you're losing that volume of the gas, but essentially you're compensating for that loss of volume with um, an increased vascular volume in the thorax. So now when you get to your maximum depth, you're at your peak of your arterial oxygen. Essentially, all the oxygen has been squeezed out of your lungs and into your tissues, into your vasculature, and you're at that peak of gas solubility. So everything is going to be diffusing into tissues, and this is where you're high risk for something called nitrogen narcosis, which essentially is when a lot of people describe it as feeling very, very drunk. The partial pressure of nitrogen is so elevated at this point, and the solubility is so high that it's going to go into your tissues, and when it gets into your cerebral tissues, it can cause things like transient amnesia, euphoria, and worsened judgment. Essentially, you're kind of drunk, but that can worsen. You can get hallucinations, stupor, coma. There's if anyone ever has read like the book Shadow Divers, which is a really interesting book about some scuba divers finding a U-boat wreck in New Jersey. They talk about nitrogen narcosis and how a lot of the divers, or how they had multiple divers on that trip who got narked, is what a lot of people will call it, and they ripped off their mask and ripped off their regulators and drowned because they were hallucinating and didn't really kind of understand what was going on. And that's typically how people are going to die from this. There's also, a risk of losing consciousness and then ceasing respirations and dying that way. And then now we're getting back to our ascent. We've gotten to our max depth. We're coming back up. At this point, because we've maximized our PaO2 and we are so vasoconstricted in our extremities, our muscle contraction is going to rely a lot on anaerobic metabolism. So at this point, if you were to take someone's labs, their lactate would be really high. And you're working really, really hard to overcome all the negative buoyancy from that water column above you and then the drag of going against the water. And so again, lactate is really high. You're shunting all to anaerobic metabolism. And the the other thing you're at risk for here, there's a couple other, these were kind of interesting, I hadn't heard about this, is involuntary breathing movements. So at this point, essentially, you can have some diaphragmatic spasms as your diaphragm is essentially contracting to try to take a breath. And when it does so, the pressure it creates in the alveoli can cause alveolar rupture, can cause shearing of the capillaries, and can cause severe pulmonary barotrauma and pulmonary edema to develop very quickly as that diaphragm attempts to contract. The other thing that they discussed in the article was splenic contraction. And this sounds a little more theoretical, but this is the idea that at this point, the spleen will contract and it will increase your hematocrit, so your circulating oxygen levels go up. So essentially, the spleen's just shunting all the red blood cells that are sequestered in the spleen, and it's shunting them all into the thorax so that they can increase your hematocrit. And in studies, they were showing that can increase about 4 to 6%. And a lot of animals that are more well evolved for this type of diving can increase their hematocrit significantly so that they can maintain oxygenation for a longer period of time. So now as we're ascending, we're getting towards the top. We're in the last 10 meters. So in the last 10 meters, you're at a really high risk of hypoxic syncope and drowning due to cerebral ischemia. And this is because of, like we said, shunting to anaerobic metabolism and oxidative metabolism, and then all of that vasoconstriction. So you're not getting a lot of blood flow to the brain. And at this point, because you've utilized most of the oxygen in your tissues, once you get to a PaO2 of around 20, that's when you're really high risk for syncope. And additionally, at this point, you have reactive oxygen species, you have presence of lactate, you have all these things going on. So the brain does not really have a lot to use for the electron transport chain to still function for you to keep moving. So there is a really high risk for syncope at this point. And now you get to the surface. You finally made it all the way back up. You swam down 700 feet, and now you're all the way back up. things that you're at risk for here. So there's something called lung squeeze. And essentially, because of all these stressors you're exposed to during the dive, the increased hydrostatic pressure, the hypertension, the vasoconstriction, all this anaerobic metabolism, it's kind of similar to what we discussed during the ascent. You're at high risk for damage to the alveoli and the pulmonary capillary beds. And this can cause an acute pulmonary edema, which increases the risk for drowning upon surfacing, because you can develop an acute pulmonary edema and essentially syncopize and drown once you get to the surface. Now, the treatment for this is just to abstain from diving. There's not a lot of studies on the time course of how long you should abstain from diving after an incident after an incident like this, but that's pretty much the treatment. And then the other thing we worry about is decompression sickness. So, as due to the high solubility of gases in tissues, you're going to get a lot of nitrogen buildup in tissues, and it can lead to a huge range of symptoms, anything from some of these mucocutaneous symptoms in the picture here, where you're getting some shearing of blood vessels, and you're getting and you can get buildup of gases in the vessels, causing rupture. You can get arterial gas embolisms, mimicking stroke or MI symptoms, and you can get, and then the classic kind of symptomatology is joint pain, because the half-life of nitrogen in your tissues is significantly longer in muscle, bone, and joint than it is in things like cerebral tissue and cardiac tissue. So it's going to sit in those joints for longer, and it's going to give you joint pain. That's why people call it the bends. There's a lower risk of developing it above about 100 meters or so, but it's still, there's always case reports out there of people getting the bends at all kinds of different depths. But once you get down to around 230 meters, that's when you have a 5 to 7% chance of, or increase in risk of decompression sickness. And that also happens to be around the depth where total lung collapse is expected due to that increased hydrostatic pressure. As far as long-term consequences go, in terms of like long-term health consequences, they've done some studies on, like, very limited studies on specific populations, because like I said, there's different populations in the world that dive for different reasons. So they studied a group of South Korean free divers who were, I believe they were diving for like sustenance, and they had a higher risk of CKD. They also did some studies on the AMA divers in Japan, and found higher risk of ENT issues like sinusitis and hearing loss. But again, there's not like a centralized kind of study showing any long-term consequences with that, aside from these specific populations. And they have done some studies in terms of looking at like FEV1, FVC ratios, and total lung capacity. And there's not really any long-term change that they've noticed in those volumes. And then, they've done a lot of studies in terms of what your labs are going to look like after diving. And, initially, after you come up, your lactate's going to be high, you're going to be acidotic, there's going to be a lot of lab derangements. But after that resolves, there's not really any long-term lab changes that they've noted. So this was the take-home message, is that breath hold diving is terrifyingly dangerous on a physiology level, but it's still a really awesome sport. So
Great job. You did a very great job covering that. Article is a kind of a broad review of the physiology and the process. So thanks for covering that. Anybody have any questions, or those who have been participating in free diving in the past, or currently any comments?
I can tell you I can give you a couple of pointers if that's okay. Justin, let me know if nobody else has anything to add. I can.
Please, most of my experience is scuba. I've only dove down while snorkeling to get a close look at stuff when I'm just snorkeling. So I need firsthand experience.
Yeah, so that was really good. That was really good review of the article. I feel like, the article is very broad. There are some points though that one could argue that one could argue the opposite, perhaps. So for example, you mentioned the article that they mentioned the 20-meter mark where you're neutrally buoyant, and that's that depends on how much weight you put on yourself and what wetsuit you're using and what thickness of wetsuit you're using. The standard, usually, if one is doing free diving for line diving, let's say, not recreational free diving, like looking at coral reef and things like that, but if you're doing line diving, usually people weight themselves so that they're neutral at around 10 to 12 meters. And that's pretty much the community standard, if you will. Even when someone is competing as well, most competitors will weight themselves so they're neutral at around 10, 11 meters, thereabouts. And you measure that by going down to 10 meters, holding your breath, and looking at your watch, and you shouldn't be going either up or down. So that's the usual community standard. The issue with narcosis is very important, and you're right, it can cause some hallucinations. Coma, I wouldn't probably mention coma in per se in the standard practice of freediving, where we go touch and return. But definitely hallucination. Well, definitely narcosis, and you feel drunk. I experimented that multiple times, and it's real. If I feel like narcosis not only can be explained perhaps by nitrogen, but perhaps by CO2 as well. Because if you, let's say, do a dive, I did a dive to 70 meters with monofin at the last competition in Dominica, and I felt some narcosis because I was propulsing myself, so I was generating CO2. But if I did the same dive by just hanging on we call it variable weight diving, you grab on the weight and just take a ride all the way to 70 without doing any movement, I felt less narcosis. And what is the difference then? Doing activity versus not doing activity is perhaps CO2. So I feel like CO2 perhaps is a enhancer for experimental narcosis. You mentioned the ascent as well, that there is a risk of pulmonary barotrauma because of involuntary contractions, or we call it contractions, right? It's because your thorax seems to contract, and that's a contraction of the intercostal muscles. In my opinion, or at least as far as I know, contrary to, let's say, diaphragmatic contractions, which are supposed to be hiccups, right? But I feel like the risk of pulmonary barotrauma is not just on ascent. The risk of pulmonary barotrauma is significant on descent. And I'll tell you after, when I give you the lecture. Splenic contraction, definitely, yeah, that's something that happens, and it's been published as well. And I feel like that's part of the basis of doing a warm-up dive. If we're going to do a performance dive, let's say you're shooting for 70 something meters. Lots of freedivers in competition do a warm-up dive, meaning one shallow little dive or two to sort of warm up mentally and physically. And I feel like a splenic contraction happens then, theoretically, to release fresh red blood cells so you can oxygenate them. You talk about drowning secondary to cerebral ischemia. I don't know if they mentioned ischemia. I probably missed it on the article, but I feel like the correct term would be cerebral hypoxia, because since you are high on CO2 on ascend, your cerebral blood flow should be higher, increase rather than not. Yeah, I feel like that was a great review. Yeah, we can touch on lung squeeze and DCS later, but that was great.
I think at some point, it doesn't have to be now. Some point, I'd love to hear firsthand reports, just what it's like to experience these deep dives on a single breath. I think it's now, but since we've mentioned splenic sequestration or splenic shift so much, the next article very much covers that. I think it's a great transition at this point. So Lee, if you can hear me, that is your article, if you are ready.
Yes, I can hear you. Hello, everyone. Give me a minute. I will pull up my slides as well. Sharing. Are you guys seeing? No. Let's see.
I can see your presentation is just not full screen.
Are you guys seeing that now? Are you guys able to see the whole screen now?
Yes.
Yes.
Okay. All right. Well, thank you guys very much. And thank you for that introduction, because it does set a lot of baseline and background information for what this study is actually trying to do. So this is actually a relatively recent article that just came out, and we'll talk about what their goals were and how we as humans, as well as some very specific world record holders, free divers, compared to our marine counterparts that do deep diving, and what that actually means about our different hemoglobin concentrations. Do we have a diving reflex? Have we adapted to become more Mammalian-like because they have these abilities? Or what does that really mean physiologically? So we're going to cover a little bit about that as to what they are trying to uncover and what they can prove or disprove. Let's see. Okay, so just as a disclaimer, everything that is being presented here is my thoughts and what I have gathered from this article itself. So we are going to, are you guys able to see the mouse?
Yes.
Yep.
Yes? Actually, let's see. Okay. Okay, so we'll cover what the aims are of this study, what they tried to look at, and the questions they generated from this. We'll go over a bit about how they tried to answer those questions by the methodologies that they went through, and how they collected that information and their results, as well as then what did they come up with, and did they actually go back to answer the questions they originally aimed, and what their findings were, and how practical it is or isn't of use for other people. So again, their question is, along the spectrum, are water seals, especially the Waddell seals, similar to humans, but specifically free diving humans who have adaptations underwater versus terrestrial animals, and what that all means in terms of their hemoglobin concentrations and the blood. And really, are they more different than, are they alike, or vice versa? Are they more similar than we initially thought? So this study was done in Europe, in Copenhagen, and as a little bit of introduction, the Waddell seal is of particular interest because of how well they are able to manipulate their diving reflexes to facilitate blood from their spleen at a decreased oxygen pressure to their heart, lungs, and their brain when they need it. And similarly, they looked at a specific group of elite breath hold divers that are quite notorious in their championships and being well known nationally, that they've definitely earned their title for being the elite breath holders in this study. And what they're saying is that they do feel as though they have similar tolerance for their hypercarbia during diving apneic episodes. And they do have note with humans that there are decreases in all of the internal chambers of the heart with deep dives, also because of atmospheric pressures that is decreasing upon them. But then they do note that in these athletes, there is a difference in their left ventricle. And one of the questions they do want to look at is, where is this blood coming from? Like the seal, their blood is shunted from their spleen. So is that something similar that we can find in our elite divers? And so with our elite divers, what they wanted to see was not just their oxygen consumption, as well as their use of that left ventricle, but where is this extra blood coming from? Is it potentially coming from their spleen like the seals, or do we have to take into consideration other parts of our bodies like the lower extremities? Because as they did point out in the introduction, the human spleen is relatively small compared to all of our other extremities. And with humans, we do have much more body surface area to have blood shunted from the lower extremities. And so what they looked at was actually quite inclusive in how they went about this. And we'll talk a little bit about that as well. And it is known that they did say that particularly it's the adult seals that have a very particular effect with the Bohr effect, with shunting and being able to offload hemoglobin and blood in apneic conditions compared to seal pups, as they haven't quite developed those diving reflexes or the mitochondrial adaptations or the hemoglobin adaptations. And so we'll be looking at all these different aspects in this article. So with those diving mammals, what's specific about the diving reflexes that they are able to essentially induce a state of bradycardia where they can decrease their oxygen consumption. They're able to withstand the pressures, and they don't have the same nitrogen narcosis like humans would be more susceptible to. They have more blood volume compared to an average 70-kilogram adult, which could be anywhere from 5 to 6, 7 to 10 being elite athletes. And with a larger blood volume, you have more blood to circulate and oxygen transport and hemoglobin. And we're going to look a little bit about the myoglobin, as well as how we offload our blood with the hemoglobin relative to 2,3-biphosphoglycerate, the molecule that is helping with the affinity of hemoglobin binding with oxygen association, or rather dissociation. And humans, unlike our mammal friends, we do actually have more extremities that we can pull blood from, whereas in the mammals, their fins don't receive as much blood and less likely to also contribute to the blood shunting that their spleen is able to. So in humans specifically, just another reiteration of this in a different picture, our human forms, we have our left ventricle that we'll be looking at with our heart. And our blood, we'll be looking at specifically the 2,3-BPG, as well as our hemoglobin levels, as well as how well we are able to use that utilizing our oxygen. And in this study, they look at the VO2 max that is induced by exercise. And what does that mean with the rest of our skeletal muscles? Are we able to use this blood somewhere else to direct it? Or are we able to also slow down our metabolism and use less blood, less oxygen, less consumption, also while apneic? So just to show another visual picture that, yes, most times very well-trained athletes' heart do have a well-formed, strong, muscular left ventricle that is physiologic and induced, not compared to someone that's elderly, not active, not someone who has hypertrophic cardiomyopathy. This is physiologic for a well-trained athlete. And this is one of the considerations that these researchers also took a look at in this article. And so specifically, they do want to mention the Bohr effect, and just to talk a little bit about what was already covered. I'll just show it in more picture forms, because anything with physics and a lot of underwater pressures, acids, acidities, and dissociation does help with pictures. So going back to the Bohr effect, that does mean that when they originally found this back out in 1904, there was a inverse relation with how well oxygen and the hemoglobin are bind together when it's related to acidic states or hypercarbonic states. And so when you have any changes to that, you either hold on to your oxygen and hemoglobin tighter, or you release it easier earlier. So the aspect that is brought about is when you are inducing hypoxia, you actually increase your ability to offload oxygen earlier, which is why when normal people go swimming, they get that sense of air hunger, drowning, and this is completely the Bohr effect, trying to help you survive. But it could be also induced and cultivated, because with the addition of using 2,3-BPG, as well as increased hypoxic states with hypercarbia, you go from the blue normal curve to this green curve, and that essentially moves you right along this dissociation curve. So what that essentially means is that for every bit of oxygen that you can hold on to, you can pretty much hold on to it longer, and for a longer amount of times before you feel that oxygen hunger state in your body and your mind and wanting to breathe. So we'll talk about this specifically because it can be induced specifically with the glossopharyngeal apneic, holding that, inducing hypercarbia to induce this increased H to get you further on this right side of the curve. So how they went about looking at everybody was looking specifically at humans first. They did choose divers as their elite divers, and they compared it to jiu-jitsu. And in the study, it was a relatively small study. They had a total of 22 participants, 11 being divers and another 11 being the jiu-jitsu members. They were pretty well controlled for their ages, as well as their ability to be for height and weight and body mass index, as well as their spleen. And none of them were pretty significant in terms of their clinical values of P. And so with this, it's not just any diver, it's not just any jiu-jitsu players. They were actually very, very healthy, very advanced in their fields. Of the elite divers, a lot of them were nationally known, if not internationally or world championships, holding silver medals or being a record holder. And the jiu-jitsu fighters were actually active fighters, except for one of them, and they were all as well nationally known and experts in their fields. And so before starting all of this, they did have a protocol to have both the divers refrain from aerobic exercise, as well as the jiu-jitsu players refrain from anaerobic exercise. And what this was hoping to do was to help sort of offset any sort of advantage one may have over the other in the 2,3-BPG measurements. And this measurement is, again, a small molecule that helps the hemoglobin when it goes to offload the oxygen at the muscle sites or the brain or wherever it's needing to go. And so what they wanted to do was to make sure that they all abstain from any activity for their appropriate levels for at least a month. And they also, with this, for both sets of participants, they did do an incremental cycling test to get what their oxygen level would be at maximum. And so this would be measured over a series of numbers, and what that would include would be just a plain rest, meaning to say they would just start from a nice warm up. They would sort of take a rest for every minute until they're exhausted. And then from there, they would take on average their maximum cycling oxygenation in increments of 30 seconds over a series of 3. So they get an actual true measurement of their oxygen capacity. And when that capacity was met, there was actually a 3 of 5 criteria where they actually had to feel physically and exertionally tired, as well as there being a respiratory exchange ratio of at least greater than 1.15. Also, they would see a plateauing of the oxygenation curve on monitor, as well as predicting and looking at their maximum heart rate for their age as predicted, as well as, again, their inability to physically maintain cycles of 70 RPMs per minute of pedaling frequency. And so it was at that very distinct point that they would measure the oxygen level. And this was, both of these measures were across all 22 participants. I do actually want to note a little bit about the 2-3 BPG measurements that they had to do. Again, this was at rest. They did, interestingly, although all 22 measurements were taken, not all 22 measurements were considered inclusive of this study. Because halfway through or partway through, they don't really give a time. They had to do a different type of assay in terms of how they collected their blood. And the first half of it was all based on the Roche measurements. They were able to, because again, we have to think of this research being over in Copenhagen, they were able to use their first set of 2-3 BPGs and have that tested locally over in Switzerland. And of that group, only 3 of the breath hold divers, as well as 4 of the jiu-jitsu players, were able to be included in that round. So that means only 7 of the 22 were being able to be included. All of those results for the 2-3 BPG were accurate. But then it did note that the company or the testing facility that they received their samples from had stopped making that Roche assay, and they had to change to the ELISA assay. And this ELISA assay had to be sent to Texas, Houston, in America from Germany. Maybe that may have had some changes to it, maybe not. We'll talk about it a little bit more in the discussion. But of this, the remaining 8 divers, as well as the 7 controls, which was pretty much a large half of the study group, had to go through the ELISA. But 1 of the divers, as well as 2 of the control ELISA assays, were not able to be collected or be reproduced. So that in essence meant they lost 3 different numbers that they could reliably use their 2-3 BPGs on. And so then going forward, now we go from 22 to only 6. And why it was only 6 of the 11 for the elite elite breath holding divers, that they don't really answer as to why either. But only 6 of the 11 were able to complete this portion of it, where they were able to measure. The other question that they had was the left ventricular mass, the blood flow to the left ventricle, as well as seeing where the blood was potentially coming from when they did a skeletal scan of the lower extremities. I'm sorry. No, this was just 6 up specifically with the left ventricle as well as the left ventricle mass and blood flow. And perhaps it had to do with the availability of the participants, or it had to do with the ability of how long they can breath hold. but it's not really indicated as to why that I was able to see that they had such a smaller group. And then again, the whole group joined again for doing the ultrasound of the spleen as well as the scan of the bones for the lower extremities. And what they really wanted to also look at was not just how things were at rest, but also compared to what the controls look like at rest compared to these elite athletes who did induce breath holding or who did induce the glossopharyngeal insufflation, which then would induce a right shift in the blood. So to talk a little bit more about the glossopharyngeal insufflation, that's what they determined as after the 4 minutes with the dry static apnea. And with glossopharyngeal insufflation, they do a series of exhalations to sort of get rid of the residual oxygen and sort of induce that the acidic state and hypercarbia so that you decrease your ability and want for oxygen. So you're able to then hold your breath longer. And please correct me later if there are any, if I'm saying this incorrectly, because I also am a diver and not a free diver. But this was how it was explained to me. And we did do a little bit of a testing of it during the DIDMS conference in San Diego. And you definitely do start feeling the numbness and tingling, the perioral blueness. But after a series of 3 of these, I did personally find that you do hold your breath longer and longer. I didn't get as long as 3 minutes. Other people had quite longer, and a lot of our champions here, I'm sure, did in our elite breath holders hold more than just 6 or 8 minutes, but they kept it at only 6 minutes. That was what these criterias were. And so ultimately, they didn't really find that at rest there was much difference between controls versus our athletes. And that was also adjusted for their age, their height, their oxygen capacity at maximum. And so this is a picture view of what I was saying. I should have gone to this earlier, but yeah, for some reason, they had the whole group together for the 2-3 VPGs as well as the oxygen. They had just a select group of only measured for their left ventricle as well as their left ventricular blood flow by this PET scan. And then they had everybody come back together on a different day to measure their spleens as well as their lower extremities. Okay. I was told that they chose the 6 divers with the longest breath hold time for this portion of the study. And so with that, they were then saying and showing this in other forms. They did end up losing one of the participants afterwards. So they weren't able to complete the ultrasound portion as well as the PET, as well as the DEXA scan for the lower extremities. But overall, they were able to keep most of everybody and get through and do most of the studies for these participants. And so for the 6, what they were measuring was before an apneic episode versus after. And what they were looking at was the size of the left ventricle. And this was done during the left ventricular mass by looking at it by the cardiac MRI. And as we can see visually, the epicardium versus the endocardium, and that was showing pretty similar, not too much of a difference. And this is the PET scan, also showing the endo versus the epicardium versus the endocardium of the heart, as well as that flow for that valuation of that PET scan. And now back to 10 participants. What was notable here is that they measured the diameter as well as the length of the spleen. And they did note that in the divers that they were a little bit different in terms of their anatomy, meaning to say that when they were holding their breaths for this scan, they would note that their spleen would be a little bit further and there would be some diaphragmatic changes, and they did try to adjust for that between the different apneic episodes. So they did have a maximum apnea episode to induce the same blood shifting dive response. And this was done at 4 minutes as well for a multiple of 4 different measurements across so that they would get a good average of the spleen in those measurements. And they would measure right before they started to take that breath. And the final part that they also compared was to also show with these numbers on the bottom is that there would be a measurement of the body in the lower portion of the legs against their bone scans. And they would measure to try to make sure that there wasn't any body positional changes before apnea and after apnea. And this, as you can see, was almost up to 6 minutes. And they measured their mass before and after. And from that, they did induce that change in grams of their blood, of the body mass, to then correlate that to to approximate milliliters of perhaps how much blood was removed or exchanged from that region. So I would say that with the way that they had set the protocol up for the study, it was very meticulous and they had very precise points in which they defined the endpoints of how they collected their data, as well as how well they tried to average and get good measurements for each individual participant to make sure it was a true average. And from all the different studies across from the initial blood collection, as well as the oxygenation of VO2 max, as well as even the PET scan, MRIs, and the body scans and spleen, it was very methodical in their collection of data. And so with that, I do feel that these results are notable, and with the very similar specialized elite group of athletes, they may also be reproducible. And so similarly, from that, they found that in the athletes, as well as the jiu-jitsu fighters, there was not much of a difference in terms of the spleen volume. So that aspect of where humans are similar or different to the seals, that was one of the hypotheses that they were able to look at and actually rule out. And they also found that similarly, the 2-3 BPG levels were similar, which they would think that if there was an improvement with offloading with the blood, that there should be a difference there, because they were saying that with the induction of apnea and insufflation with the glossopharyngeal, that they would induce hypercarbia as well as acidosis. They should expect that the 2-3 BPGs would be different, but in fact, it was actually the same between the free divers and the jiu-jitsu fighters. But what they did find was that in the divers, there was an increased amount of hemoglobin concentrations. And so with this, so in keeping in mind that, again, the DEXA scan as well as the ultrasound, this was for both groups of both control and the elite athletes, the divers. And notably, I do want to point out that at rest, the total grams was 23,792, whereas in the apneic group, there was only a difference of about 200 or so. So interesting. The other thing that was also notable was the spleen volume as well, and that was at rest 230 versus at apneic periods, and that would be 128. So I feel as though with the conclusions and the discussions with this is that with divers, it can be induced that they are more similar to the seals, but only in certain ways. But not in the same way that they originally thought about the spleen providing more blood to the left ventricle, as they originally thought that the seals would have, as most of the blood does come from the lower extremities. But what was actually notable about this study was that it did, for the first time, show that there was blood shunting and blood shifting in divers, and that this was the first time they were able to see something similar in elite divers as well as other diving mammals, because it was able to be induced during their maximum apneic periods that they were able to see this. And that can account for the change in the hemoglobin as well, because they did have similar elevated levels of hemoglobin and concentrations with diving mammals. And they also did note that, again, this blood shift was from the lower extremities, not the spleen, as it in fact actually decreased blood from the spleen, whereas there was an increase from the legs. So that difference of the 23,700 something grams versus the 27,500 something grams in that DEXA scan, they attributed that difference in weight to be approximately that much of blood volume that was shunted away during that time. And so I think the interesting thing about this is there are limitations because it is such a small group of very specific athletes. And they did note that the limitations to this, as well as recruitment of more participants, was limited by the period of apnea being at least 5 minutes. And they did also say that if they were able to take this study and do it prospectively, that this could potentially give them more information as well. But these are their limitations, and they did try to attribute that to their smaller group, but they tried to also use that by the way they calculated their results. They did talk about a specific power that they tried to account for these numbers and errors with the smaller group based on their prior studies that they had done with their research. And that's how these numbers were shown on their table. So ultimately, I think it was a very interesting study. It gave us a lot of information, but then the realities of it is I'm not really sure how well this does or doesn't really change and what the reality of that looks like with freedivers. And so I'm very glad that we do have a large group of people here that are either interested or divers or freedivers that can potentially share their thoughts on this, as well as their thoughts on this article. Is like, is it really helpful? Did it give you any clarifications as to, oh, well, I'm actually able to breathe more because physiologically all of this is happening and there's a light bulb moment? Or it's like, well, okay, this was interesting read and an interesting study, but is that just because it was a very select few groups that happen to have very good mechanics and physiologic conditions and adaptations? Or can we all really say we're just like seals if you get to that level? So yeah, I will leave that as a thought and a discussion for everyone, and please let me know if you guys have any questions. I'll open it up. Thank you.
All right, thank you for covering this article. It was a pretty tough one. It was a pretty dense one, and it sort of consisted of like 3 to 4 mini studies within itself. So
Yes.
it was a pretty niche article and one that definitely got into a wide variety of physiologic processes. So thank you for covering that. I tried to make some comments in there, trying to clarify some things as you went.
Thank you.
Basically, I just saw my earlier comment. 6 of the divers with the longest breath hold times were used for the sub studies. Let's see, and at that point they weren't involving the jiu-jitsu athletes at that point because they don't do the freediving. I did some math based on the density of the blood. I don't think it really plays much of a role. I don't know where they got 268. It should have been 248, but it's not too big of a difference. And then when you're mentioning that the spleen is smaller, that would indicate that it has shifted or shunted or released blood, whatever you want to call it. So smaller spleen during this type of study or activity indicates that it has been shifted out. So that was just one thing I noticed that might have been interpreted in one of your slides. So there's really a lot of physiology covered. Does anybody have any questions? And Dr. Valdivia, I would probably like your help on that. And I think I see PJ Gregory too, is a Duke hyperbarics fellow. So if either of you could field some questions, that'd be great. Any questions for either them or Lee?
That was a great article, great review. You know, it may seem very dense, but it does explain a lot of what we do in freediving. And an article like this, you'll be surprised that if non-medical, non-scientific background freedivers will be joining in, they'll be having popcorn and trying to like explain how explain what we do in the water translates into science. But it's very important what you mentioned, that the conclusion is that there's a lot of blood shift from lower extremities. And that makes sense, because if you, let's say you do a dive in free immersion, perhaps, which I'll show you shortly, where you're pulling from the rope without moving your legs, you will feel your legs ache as you're coming up. You'll feel changes on your legs. You feel somewhat lactic, and you wonder why, because I'm not using my legs, I'm not kicking. It's probably because significant vasoconstriction on your lower extremities. So that's interesting. The changes in heart volume are definite, and they're not just exclusive to when you're underwater. As I'll show you a fluoroscopy of my own, where my heart volume almost doubles when I'm on a dry breath hold. But it was great. That was a great article, and definitely the physiology is important. You will hear probably, if you connect to the freediver chat groups or the groups on Facebook, there's discussions over discussions, endless, about hemoglobin, left shift, and things like that from people from all over the world. So this is a really good discussion. So you mentioned the Bohr effect, actually.
No,
go ahead.
No, I just thought it was interesting. I'm not sure how they made the decision to choose jujitsu. I think it was jujitsu, right? Athletes. I just thought that was interesting. Is that common that you've seen in freediving articles, or comparing apneic to? It was just interesting. There's so many, track, field runners, swimmers. I just thought it was interesting.
Yeah, I don't know. I mean, I don't do jiu-jitsu, but I can only imagine jiu-jitsu as some anaerobic component, where endurance is important, and mental, and perhaps there's some similarities. to
Yeah.
draw.
I almost wonder if one of the authors was in a jujitsu club or something. And he said, "Hey guys, I'm doing this study. I need some athletes. Like, you guys want to come in and let me scan you on Saturday?"
Maybe.
And Dr. Valdivia, you were mentioning the Bohr effect before I cut you off.
Yeah, the Bohr effect is something that plays a role in safety, because if you're not a freediver and you're going to your 101 course, the most important thing is the most important message is do not freedive alone. Freediving, myself, from my background, I'm a competitive freediver, and I'm the medical director of the USA Freediving Federation. So my job is to tell everyone to not freedive alone. That can take your life. It can kill you. It can kill you in your bathtub if you don't do it right. And in fact, we published a paper about 2 or 3 years ago on the dangers of dry breath hold in your couch. If you hold your breath alone in your couch and you happen to think that it would be cool to wear a mask or a nose clip, you can die. So it's no joke. In the past, let's say 10 years ago or 9 years ago, when I started freediving, people say, well, you can do static apnea in your bed, and if you black out, it's okay because you're in your bed. You'll wake up. However, if you are hypoxic and you're in your couch and you're alone and you're hypoxic already, your awareness is impaired. Therefore, you cannot take your mask out. You will try to breathe through your nose, and then you're gone. So that's the most important thing in freediving, is don't dive alone. And the Bohr effect is another big message, is don't hyperventilate. Hyperventilation, especially unconscious or inadvertent hyperventilation, is a real thing in freediving, where if you, let's say, the usual way they teach in the most current, let's say, agencies for freediving is to not control your breathing, as if you were doing tidal volume. And any attempt to control your breathing can result in hyperventilation. Hyperventilation is any change that will drop your CO2, right? And that gives you the shift, and that perhaps gives you higher chances of blacking out. But very important that if you mentioned, if I teach you freediving, and let's say if I'm your instructor the first day and I teach you how to hyperventilate, you probably will think that I'm the best instructor ever, because I'll increase your breath hold from 45 seconds to 3 minutes, because your contractions will be gone and your urge to breathe will be gone, and you'll just plow through it and you'll say, you're my sensei. But if I teach you the same and I have you do a depth dive, that's going to cost you. It can cost your life. So there's different ways to approach freediving, and my recommendation is try to not hyperventilate ever, unless you're with a coach and trying to do a very specific part of freediving, which is competitive static performance. There's some specific instances where if you're competing for static records, there's some component of hyperventilation there, but not in depth diving. You also mentioned glossopharyngeal insufflation, and that's something we call packing. Popularly, we call packing in freediving community, where you use your mouth as a pump, and you can inhale to total lung capacity, but then we tend to want to have more volume beyond total lung capacity when you're going deep, or sometimes even to a degree in pool disciplines. So glossopharyngeal insufflation is this. I'm going to show it to you. We use the nose clip, and when we go beyond TLC, I mean, some people more than others, but I could pack probably 1.5 liters beyond my total lung capacity doing this. So that is glossopharyngeal insufflation, and that allows you to just get more tank, if you will. it's cool that you mentioned that. So I wanted to make sure everyone understands what that is or what that looks like. And there's another way to do dose-of-friendly ionization, which is reverse packing, which is the opposite. And the opposite would be to go below your residual volume. If you exhale, you get to residual volume where you cannot exhale anymore, but you can get deeper than that if you do the opposite, which is this one. And that is another way to do glossopharyngeal insufflation. But yeah, go ahead, Justin. You're going to ask a question.
There was another article, I think I put it in the Google Drive folder under further reading, and it's sort of mentioning like the depth at which there would be total lung collapse for a non-trained diver, not using glossopharyngeal breathing, not using things, just like the natural way to do it. And then you just add on the techniques like glossopharyngeal breathing and then the reverse lung packing, and then how much further down you could go based on the physiological changes you would get with that. So that was really interesting. Still hard to imagine how to actually do that. But with the reverse, when you're doing that at depth, are you releasing the air from your nose, or is it coming? Oh, you have the clip on, so it must be coming out of your mouth then, correct?
We don't do reverse packing when we are doing a deep dive unless in very specific and controlled circumstances where people are doing specific training for competition. And it has a risk of lumbar trauma because you're going below your residual volume. So there is a risk of a lot of things when you go on residual volume. Most people just do normal full inhale, total lung capacity.
Okay.
Yeah.
I think at this point, we could probably transition to more of our to Dr. Del Divio's presentation at this time. So he has some sensitive content in his slides that's been provided by others. So to avoid any conflicts, we're going to end the presentation as far as recording. Everybody, please stay along. We're going to continue, just not going to be recorded anymore. So if you're here, you'll be the only one seeing it. Otherwise, just for the recording's sake, I'll see you all next month. We're going to be transitioning a bit to water treatment. So staying in the water, but focusing on how to safely treat water for like backpacking and things like that. I'm going to end recording and then we'll continue in just a second.
Well, let me share